Hi guys, in the previous lecture we have seen the rectifier classification. Also we saw how to find the RMS value of any rectangular function. Now in this lecture we will see the rectifier circuit. So I already explained you that I divided the rectifier into categories. First one is the single phase, second is the three phase. In single phase, half wave and full wave, and in half wave again it is divided into categories: uncontrolled, in which I will use diode, okay, and in control I will use thyristor. So in this lecture, that is lecture number 9A, we will see single phase half wave diode rectifier, that is uncontrolled rectifier. So we will see in this lecture single phase half wave uncontrolled rectifier for R load and L load. Got it? So let us proceed to the first slide. So this is the single phase half wave uncontrolled rectifier, okay, in which we are giving AC input and we are getting DC output. So what I am doing, I am connecting one diode and I am converting AC signal into DC signal. Let us see how. See here, this is nothing but diode circuit with R load. So supply is Vm sin omega t. So Vm sin omega t will somehow look like this. From 0 to pi it will be positive, and from pi to 2 pi it will be negative. Now when anode potential of this diode is, this is anode potential and this is cathode potential. So when anode potential is greater than cathode potential, then this diode will be shorted and it will start conducting. So from 0 to pi, this Vm input supply, let us take this is Vs is equal to Vm sin omega t, input supply is greater than 0. So if input supply is greater than 0, then this diode will be shorted and we will get output voltage that is equal to the input voltage. So V0 is equal to Vs from 0 to pi. Now when the supply voltage get reversed, means supply voltage will be somehow like this. This will be plus and this will be minus, and now the diode is connected with R load, okay. Now when the supply, initially it was from plus to minus, then this diode is shorted and we are getting output voltage that is following input voltage from 0 to pi. So from 0 to pi, output voltage will follow the input voltage. Now see, from pi to 2 pi, this input supply get reversed. So it will be something like this, from minus to plus. Now this diode will be reverse bias and it will be open circuited because the anode potential is connected with negative and cathode is positive. So anode is negative and cathode is positive, means reverse bias condition. So the diode will be open circuited, and in this case V0 is equal to I0 into R. Since it is open circuit, so I0 will be 0, so V0 will be 0. So we can say that from 0 to pi, V0 is equal to Vs is equal to Vm sin omega t, okay, and from pi to 2 pi, diode is open circuited because of reverse bias condition, so output voltage will be 0. So from pi to 2 pi we are not getting output voltage. Since it is a voltage steep type of load, means output current will be similar to the output voltage, okay. So output current I will get that is equal to Vm upon R, V0 upon R, and it is similar, the waveform is similar to output waveform. From pi to pi the output current will be 0, okay. Now see the voltage across diode. From 0 to pi the diode is conducting. Diode is conducting means it is shorted. So it is shorted means voltage across the diode will be 0, and from pi to pi it is open circuited. So circuit will be somehow like this. The circuit will be like this and it will be open circuited. Now you have to find the voltage across diode. So voltage, if you will apply KVL, then the voltage, output voltage is 0 and voltage across diode will be equal to the supply voltage. So voltage across diode will be equal to the supply voltage from pi to 2 pi, okay, and it will follow the input voltage, that is the supply voltage. So if I will ask you what is the peak inverse voltage of diode, then peak inverse voltage will be Vm. It will be always be in positive. Got it? So in this type of rectifier we are getting output voltage only from 0 to pi, and from pi to 2 pi we are not getting output voltage. So in one cycle we are getting only one pulse. So this type of converter is known as one pulse converter, okay. Now take a note. and this note is very useful in all type of rectifier. I will derive these all note in all type of rectifier by considering R load, L load, RL load, RE load and RLE load, any kind of load. So first note is, what is the output voltage, average output voltage of this waveform? The average output voltage I will get, that is equal to 1 upon T 0 to T V0 dt. Okay. So average output voltage will be 1 upon T. What is the time period of this waveform? The time period will be 1 upon 2 pi. And for how many period it is we are getting output voltage? From 0 to pi only. From pi to 2 pi we are not getting output voltage. So 0 to pi, and it is equal to Vm sin omega t, d omega t. So find the average output voltage, you will get that is equal to Vm upon pi. Okay. Now second is I naught average. So what will be the I naught average? I naught average will be V naught average upon R, that is equal to Vm upon pi R. Okay. Now the third point is V naught RMS. So V naught RMS, you have to find the RMS output voltage of this waveform. So RMS output voltage will be under root of 1 upon T 0 to T V naught square T dt. Okay. So I can find RMS voltage like this. 1 upon time period of this waveform is 2 pi, and we are getting output wave voltage that is from 0 to pi only, and V0 square T dt, from 0 to pi it is following Vm sin omega t. So we can say that Vm square sin square omega t d omega t. This is the RMS output voltage of this waveform. Now V0 RMS is equal to under root of 1 upon 2 pi, take Vm square outside, okay, 0 to pi, and sin square omega t d omega t can be written as 1 minus cos 2 omega t by 2. This is d omega t. So solve this integration, you will get output RMS voltage that is equal to Vm by 2. Okay. This is the third point. Fourth point is I naught RMS. So I naught RMS, since it is a voltage steep up type of load, so waveform of I naught and V naught are similar. So we can say that I naught RMS is equal to V naught RMS upon R. Okay. Now the fifth point is P naught. P naught is the output power. So I already explained you how to calculate the output power of any voltage steep type load. Since it is voltage steep type of load, so output power will be V naught RMS square by R, or you can say that I naught RMS square into R. We have to take RMS voltage and RMS current for finding the output power. Okay. Sixth point is input power factor. How to find the input power factor? So for finding the input power factor, what you should do, you should make input power is equal to output power. Since it is a power electronic circuit, so we are taking the case of ideal diode, so losses in the circuit will be 0. So input power will be equal to output power, and input power we can write like source RMS voltage, source RMS current into cos phi is equal to output power, that is equal to I naught RMS square into R. Now here source RMS current is equal to output RMS current. See, if I will make the waveform of source RMS current, then source RMS current I will get when this diode will conduct. So when this diode will conduct, then output waveform, output current waveform is somehow like this, that is equal to source current waveform. So RMS value of source current is equal to RMS value of output current. So we can say that IS is equal to IOR. Waveform of source current and waveform of output current, both are same. That's why RMS value, their RMS value are equal. So I can write finally cos phi is equal to IOR into R by Vs. Okay, and IOR into R is nothing but output voltage, so VOR upon Vs. So if I will ask you what is the input power factor of this circuit, then no need to remember this formula VOR upon Vs. You don't have to remember this, only you have to put the input power is equal to output power and see whether source current is equal to the output RMS current or not. If source current is equal to output RMS current, then cut the source current equal to IOR and then find power factor. Got it? So input power factor will come out to be VOR upon Vs. Now 7th point is conduction angle of diode. Conduction angle of diode. Conduction angle is denoted as gamma, and conduction angle of diode we can easily see that conduction diode is conducting from 0 to pi. So conduction angle of diode is pi. Okay. 8th point is extension angle. Extension angle is defined as up to what angle the diode is conducting. Here up to what angle you are getting current? You are getting current up to pi. So extension angle is equal to pi. So beta will be pi. In this case, conduction angle is equal to extension angle. But when I explain you the controlled rectifier, then there you can see that conduction angle is not equal to the extension angle. In this case, in all the diode rectifier, the conduction angle is equal to extension angle. Extension angle is defined as up to what angle you are getting current, that is the extension angle. But conduction angle is up to what angle the diode is conducting. So here the extension angle and conduction angle both are same. 9th point is peak inverse voltage of diode. So peak inverse voltage is nothing but Vm. Okay. And 10th point is circuit turn of time. Circuit turn of time is defined as the time for which the diode is in reverse bias. So I can define the circuit turn of time like this: time for which diode is reverse bias. Here I am taking P devices as a diode, so circuit turn of time is defined as time for which diode is reverse bias. If I will take thyristor in the place of diode, then what will be the circuit turn of time? The time for which the thyristor is reverse bias. Here the diode is reverse bias from pi to 2 pi. So what will be the circuit turn of time? Omega Tc will be equal to pi. Angle at for which the diode is reverse bias, that is pi. So Tc will come out to be pi by omega. So these all point I will derive for every type of converter for different type of load. That's why I have taken as a note so that it will be easier to remember. Got it? So that's all about R load. Now see the L load. Okay. Here also the input is Vs is equal to Vm sin omega t. Okay, and I am attaching one diode and load is inductor. So from 0 to pi the input supply is positive, so this diode will conduct. So let us say that diode is conducting. Okay, so when diode will conduct, then what will be the output voltage? This is the output voltage. Output voltage is equal to input voltage. So when diode will conduct, output voltage is equal to input voltage, that is equal to Vm sin omega t, and output voltage is nothing but voltage across the inductor, that is equal to L di by dt, that is equal to Vm sin omega t. Okay, so di is equal to Vm by L sin omega t dt. Integrate from 0 to I, and here from 0 to omega t. I don't know up to what it will conduct, so I will take omega t. Okay, so it will come out to be Vm upon omega L 1 minus cos omega t. This is the current I am getting when I will take purely inductive load. So here the current I am getting Vm upon omega L into 1 minus cos omega t. If I will plot the waveform of this it, then I will get something like this. From 0 to pi 2 pi it will be somewhat like this. So what is the conclusion? The conclusion is we are getting current from 0 to 2 pi, means the diode will always conduct if I will consider the L load. See here, when diode is conducting, then output voltage is equal to input voltage, means output voltage will follow the input voltage. So when diode is conducting, means output voltage will follow the input voltage, similar to input voltage. Got it? But current we are getting from 0 to pi, means we are getting current for all time, right? So conduction angle of diode is 2 pi. If I will tell you what is the conduction angle of diode, then conduction angle of diode is from 2 pi. And what is the voltage across diode? Since diode is conducting for all time, so voltage across a diode will be 0 for all time. Got it? So when I will take purely inductive load, then current I will get from 0 to pi, and it will get maximum at pi, the current will get maximum at pi. Put omega t is equal to pi, you will get it is equal to 2 Vm upon omega L. Okay, so this is not Vm upon R, this will be 2 Vm upon omega L. The maximum current I am getting 2 Vm upon omega L at pi. Okay, here I want to explain one point. See here, from 0 to pi, V naught greater than 0, output voltage is greater than 0, and I naught is also greater than 0. What do you mean by this? It means power is transferred from source to load. Okay, when P naught is greater than 0, output power is greater than 0, then means the load is taking power from the source. Okay, now see from pi to 2 pi what is happening. From pi to 2 pi, V naught is less than 0 and I naught is greater than 0. So overall P naught will be less than 0. So in this case, power is transferred from load to source. When P naught will be less than 0, means the load is transferring power to the source. How is this possible? See, I am going to explain you from network point of view. If you have studied my lecture, that is the transient lecture from lecture number 13 to 16, then you can understand that from 0 to pi, this power is transferred from source to load, means this source is giving power to this inductor. So from 0 to pi, the inductor is charging, and from pi to 2 pi, the inductor is discharging. So from 0 to pi, the source is delivering power to this load and inductor is charging, and from pi to 2 pi, the inductor, whatever the energy present in the inductor, is get again transferred to the source, because here no bloody resistor is present. So if there is no resistor present in the circuit, means whatever the energy present in the inductor will again fed back to the supply from in between pi to 2 pi. Got it? So whenever the inductor is present in the circuit, then no matter what is the polarity of input voltage, source voltage, the diode will conduct beyond pi. So here the diode is conducting till 2 pi. Understood? There is another way of explaining this like this. If you have studied my transient lecture, then from 0 to pi, source is delivering power to the load, means inductor is charging. Now from pi to 2 pi, this inductor is behaving like a current source. Okay, this inductor is behaving like a current source, and this diode is sorted from pi to 2 pi. Means this inductor is behaving like an active element, and it is transferring power. Whatever the energy present in this inductor is transferring power to the supply. Got it? So in this way we can explain what is happening here. From 0 to pi, power is transferred from source to load. From pi to 2 pi, since output power is negative, means power is transferred from load to source. Okay, now again derive all the things that we have derived for R load. Take a note. What will be the V naught average? The V naught average, since output voltage is equal to input voltage and it is sinusoidal, so V naught average will be 0. I naught average will be Vm upon omega L. We have already find the IT is equal to Vm upon omega L into 1 minus cos omega t. Here I naught and V naught are not same, so I naught average I am getting and V naught average I am not getting, that is equal to 0. So IT is equal to Vm upon omega L into 1 minus cos omega t. Find the average value of this IT. This is I naught t. I naught average will be Vm upon omega L. Okay. What is V naught RMS? V naught RMS, since it is sinusoidal, so V naught RMS will be Vm by root 2. Okay, and I naught RMS we can find by using this equation. No need to find, because nowhere is asked about the RMS output voltage in case of purely inductive load. Okay, this is first point, this is second point, this is third point. Now fourth point is, what is the conduction angle of diode? So conduction angle of diode for all time, diode is conducting for all time, so we cannot say conduction angle of diode is up to 2 pi only, we can say for all time. Okay, and what is the extension angle? Extension angle is up to what the current we are getting. So current we are getting up to 2 pi in one cycle, that is beta is equal to 2 pi. Okay, circuit turn off time will be 0, because for any time period the diode is not getting reverse bias. Diode is always conducting because of this inductor, purely inductor. So circuit turn off time will be 0. Understood? So this concept is very important, that is from 0 to pi output power is positive and from pi to 2 pi output power is negative. Means from 0 to pi the source is delivering power to the load, and from pi to 2 pi the load is delivering power to the source. This concept is very important. You will get lots of numerical based on this, so you have to understand this. So that's all about this lecture. In the next lecture, we will cover RL load and RL with freewheeling diode. So if you guys understood the concept, then please like this video and subscribe to this channel. For doubt solving, you can join our Facebook group. Thanks for watching this video.